Okay.
All right. On cue. So hello and welcome. I'm Professor Sean Tavalia, Academic Chair for Physical Sciences at Suffolk County Community College and founding member of the board of the Hamptons Observatory. For nearly 20 years now, the Hamptons Observatory has been dedicated to promoting an understanding of and appreciation for science through free quality educational programs such as tonight's event. This event is co-sponsored by Suffolk County Community College's National Science Foundation-sponsored iSuccess program, a program that provides scholarships and extracurricular activities for students enrolled in STEM fields. Although this event is free, it could not be possible without the generous donations of people like you. For more information on how you can donate, please visit the Hamptons Observatory website, which I believe Donna will put in the chat. If tonight's program inspires you, please consider enrolling in one of the many traditional or online astronomy courses at Suffolk County Community College. It's a great place to be. During this talk, we ask that you keep your microphones muted. If you have questions during the talk, please pop them in the chat. At the conclusion of the presentation, we'll try to address all questions. Now, tonight's speaker has led the development of heliophysics as an integrated scientific discipline from which fundamental discoveries about our universe provide direct societal benefits. She made possible flagship missions, such as Solar Dynamics Observatory, Van Allen probes, Solar Orbital Collaboration, Parker Solar Probe, and the Stereo Solar Observing missions that would revolutionize our understanding of how the sun shapes space weather in our solar system. Since 2017, she has been the driving force at NASA headquarters and NASA Ames behind the growth of Frontier Development Laboratory, both in terms of the breadth of problem areas tackled, as well as the number of agency and industry partners included. She is currently a senior advisor for new initiatives at Goddard Space Flight Center and program scientist at NASA's Heliophysics Division. Please join me in welcoming Dr. Lika Guhathakurta. Lika, it's all yours.
Thank you, Sean. Well, I think you have named all the missions, and you will hear them from me again.
Sure.
And I guess I'm looking at this talk as really describing the program Living with the Star, and that science that matters to people. Oftentimes we forget that sun is a star simply because it's the only star that shines during the daytime. So in this picture that you are seeing, and I think it's there's a movie, Sean, which is the Earth, where you will see the shadow of the eclipse actually. So, Earth might seem isolated in space, but it is deeply connected to the sun. Nothing could be further from that truth. Earth is profoundly connected to our star. That is the first message. The bright blue disk that we just see is the most obvious evidence that we are connected to this star. So there is a continuous flood of sunlight that warms the planet, as we know, simultaneously allows us to live and see. But there are invisible connections as well, which are equally profound, the ones we cannot touch, cannot feel. Solar radiation, photons, puffs our atmosphere, altering its structure and chemistry. Solar wind.
I feel like, Susan, you're probably the one that communicates with them the most. Yeah. More than me.
Dr. Lika, you got muted?
Yeah, can you hear me?
Yeah, you're good.
Okay. And so then there is solar wind that really buffets our magnetosphere, lighting up our polar skies with curtains of light. talking of light, the aurora borealis and australis. I hope some of you saw the spectacular shows from May and the past couple of months. It's been just incredible. But then it also drives currents of electricity through the soil below. Solar magnetism deflects cosmic rays that are produced not in our solar system, but in faraway galaxies, and moderating the effect of the galaxy basically on our tiny home in space. That's what the sun does. And so this is a picture from 2017 eclipse, and I hope you saw that eclipse, total solar eclipse. If you didn't, I hope you saw the one in 2024 in April. And I think we'll go to the next slide, which is actually an audio of mine from 2017, talking about the inspiration from solar eclipse and the sun-earth connection.
An opportunity to sort of transform us in a way, especially the younger generation who will re-experience it in America in 2024 in a very profound way. I mean, this eclipse has an opportunity to tell people that science works, the methods of science works. We can predict this event. We can predict future events. You can teach about basic geometry of what's happening during the eclipse. You can talk about our endeavor to find exoplanets, that the techniques we use in detecting exoplanets in far, far away solar system is nothing but, you know, that particular moon in another solar system or a planet sort of casting a dip in the stellar brightness. So, you know, if we can take people closer to that with real examples, I mean, what's better than?
And I really hope that many, many of you actually got to witness this eclipse of 2024. America has been incredibly lucky to have two such great eclipses. But if you haven't, eclipses happen about every 18 months on some place on this planet, and you should take yourself there. Next, please. So, you know, we can ask the question, why do we do science? Why government agencies fund science? It's a curious question that was looked at by Donald Stokes from Woodrow Wilson School for Public and International Affairs, Princeton University. And he said that all research can be plotted on two axes, curiosity versus utility. The result is three distinct classes of research. Pure basic research, which is exemplified by Niels Bohr, early 20th century atomic physicist. There is pure applied research, exemplified by work of Thomas Edison, the inventor. And then there is user-inspired research, described here as Pasteur's quadrant. Living with a Star program is unique among NASA space science program, not Earth science, space science programs, because it was designed to occupy the Pasteur quadrant, which is an equal mix of curiosity and utility. Next, please. And so what is the goal? Understanding the sun and its interactions with the Earth and the solar system, solve fundamental mysteries of heliophysics, understand the nature of our home in space, and build the knowledge to forecast space weather throughout the heliosphere. And this is the journey that I will take you along. Next, please. So let's start with the Sun-Earth system. You know, the Earth orbits inside the atmosphere of the sun in that sense, we truly are living with this star. Even though to the naked eyes, the sun appears to be a constant, it is only a limitation of human eyes because we can only see light in visible, not in X-rays, not in extreme ultraviolet, not infrared, right? So in visible, it is constant. But modern telescopes and spacecraft have penetrated the sun's blinding glare and found basically a maelstrom of unpredictable turmoil. And we've been doing this for the past 35 years, I would say. Now, this picture, this is a prototype for studying the sun planet. One in particular is Sun Earth that you're looking at that we can study in great detail. The distance between Sun and Earth is no joke, 93 million miles. It's for most of us, it seems unfathomable. You can fit millions of 1 million or something like that of Earths into the volume of the sun. What are some of the basic things, right? The sun is coupled to the planetary system and by space radiation, which are called photons, charged particles, electrons, protons, sometimes some low mass atomic nuclei, and magnetic fields. And magnetic field will be a theme again, the most important thing that drives this whole system. Now, like anything else, the study of heliophysics involves three forces and their interactions: pressure, gravity, and magnetic field. Now, pressure and gravity we are very used to, right? I mean, terrestrial weather is driven by that, not space weather. Space weather is driven by magnetic fields. And you can see essentially each one of, I mean, this is just a cartoon drawing. On the right-hand side, you see Earth with its magnetosphere, and you can see the different layers of atmospheres we have. The surface, atmosphere, ionosphere, plasmasphere, magnetosphere, kind of quite a few, right? Not all planets actually have that. And so therefore, sun's interaction with those planets are different. Next, please. So, well, those are just arrows pointing to heliophysics. And the little curvy thing on top, they are actually the cosmic rays coming from extrasolar system. They are created outside of our solar system from death of stars, explosion of nova, supernova. Next, please. So where did we begin, or where do I want to start? Our understanding began as a human species with a very local view. And as technology developed and international coordination grew, we began to view the Earth as more of a system. And so heliophysical in that sense is a broadening of the concept geophysical, which is studying the Earth as a system, extending the connections from the Earth to the sun and interplanetary space. It is the domain of the sun. So if you can see on the x-axis time, 1883 was the first International Polar Year, one. That's the first time we started actually looking at the North Pole with all the instruments we could muster. Magnetic field, magnetometer measurements were big in those days. Then came 1933, International Polar Year 2, where, of course, the field grew, the scientific community grew, more international cooperation. We started looking at both poles of the sun, of the Earth. And then came the big one in 1957, the International Geophysical Year, which really changed the landscape, I would say. And that's when we started looking at planet Earth as a system. So it seems like it's a natural progression that we are going outward, that the next 50 years after IGY, we would start International Heliophysical Year, which was approved by the UN
Yeah,
in 2007.
that's what I said.
Next, please. So this is a little bit about, I know this is an audience with mixed crowd, so I have added sort of mixed ideas. Somebody might get something out of it. So this is a concept about organization of the universe. You know, we kind of sort of box ourselves into astrophysics, planetary science, earth science, heliophysics, and no one really understands what many of these things mean. So let's start off by saying that the universe is filled with electrically conducting gas, that is ionized gas, that we call plasma. Plasma is the main focus of heliophysics. What are the exceptions? The exceptions are planetary atmospheres, and we live in one. Otherwise, we wouldn't be who we are. And the other places are some dense interstellar clouds. So in essence, we live in a magnetic universe. We may presume that most stars are magnetically active like the sun, but the sun is the only star available for direct study. So we do study it in great detail. And so how do we sort of divide this universe between stars and sun? Because sun is a star after all. So there's this concept of gravitationally organized matter, like planets, stars, galaxies, and magnetically organized matter. You know, that's the plasma astrophysics, like sunspot, magnetospheres, stellar and galactic spiral fields, galactic plumes, you name it. Now, the gravitationally organized matter, they create solar systems, planetary systems that lead to, you know, origins question, life on planets. On the magnetic organization part, we have plasma physics, solar connections, and we look at destinies, life around and between planets. What make life possible? Next, please. So this is basically, no, the previous one. Or is this the next one?
Should be.
Okay. So this is solar wind interacting with Earth's magnetic field. Fascinating, isn't it? Sun has its own magnetic field, Earth has its own magnetic field, and they each other can dramatically alter what impact we feel, basically. So magnetism describes virtually every feature on the sun, right? From sunspots to these soaring structures. Prominences can easily reach height of a solar radii. We've seen those pictures from Solar Dynamics Observatory. It is well known that solar activity related solar wind disturbances can energize processes occurring in the space around the Earth, especially magnetosphere, thermosphere, ionosphere. Solar wind interacts with Earth's magnetic field. So we, of course, live in the outer atmosphere of this star. Fortunately, we live under a sort of umbrella provided by our own planet's magnetic field, the magnetosphere. It's the lower right-hand corner picture. Can you play that movie? And unfortunately, the magnetosphere always isn't a reliable shield. And so what you're seeing there is essentially a computer simulation of Earth's magnetosphere under the pressure from solar wind. And it quivers like a cocoon. And the magnetic field, Earth's magnetic field has north-south, just like any other magnetic field. And that is the leaky part. Sometimes when there is connection between Earth's magnetic field and sun's magnetic field in the right orientation, particles can penetrate. And that's when a lot of beautiful stuff can happen, like the northern lights, southern lights, or other deleterious impacts can happen too. Next, please. So this is a very complex system with many different temporal and spatial scales. The system is multi-scale and it couples between scales. I mean, it's hard to explain. You're kind of looking at from the core of the sun to, ionosphere, thermosphere, mesosphere. These are the structures you're looking at, right? So the heliophysics domain spans the heliosphere, right? From core to 5 billion miles beyond Pluto, where the sun's magnetic field essentially meets up with the interstellar space. And this vastly complex region requires understanding of physical processes that's 19 orders of time magnitude, 25 orders of spatial magnitude, encompassing interactions between solar and planetary atmospheres and the interplanetary medium. So it's no walk in the park. We don't have enough observations to understand these. Neither do we have computational resources, but we do the best we can. Next, please. And so this is the complexity of geospace. I showed you the sun, but everything that the sun is producing, radiation, photons, particles, magnetic fields interacts with the various layers and the magnetic field of our own planet. So predicting space weather is more challenging than forecasting hurricane due to its vast complex system. That's very clear. So to give you an example, if the sun were the size of a basketball, Earth would be a pinhead at the other end of a full-length court, illustrating the scale and distance involved, basically, these two, right? So researchers often lack the precise data when that is the kind of scale we are working with to predict if a solar storm will generate geomagnetic currents, if a solar storm will hit our planet. So the impact of a coronal mass ejection, solar storm, depends also on its magnetic field polarity, which can only be determined again when the storm is very close to Earth, about 1 million miles from Earth. So this is a complex process, and we have understood it greatly in the last 20 years, but there's so much more to learn. We are so much behind when we compare ourselves to the terrestrial weather forecasting world. Next, please. These are going to be some quick pictures. This is a coronal mass ejection impacting Earth. This movie shows, massive breaking from the sun and traveling through space where they impact Earth's magnetosphere. And most of the particles are deflected by Earth's magnetic field. That's why we call it a shield. But that really depends on the orientation between the two fields. But again, as I said, if the field lines orient the right way, then the particles can penetrate through the open field lines in the poles of our Earth. Next, please. I'm not going to complete the picture. These are beautiful. This is what you're looking at, is the cocoon, the magnetosphere of the sun. So this is the impact of the solar storm. Another kind of quick picture to show, solar flares, particles, coronal mass ejections reach Earth at various speeds, affecting systems like radio communications, satellites, power grids, astronauts doing extravehicular activities, precision agriculture, drilling of oil, pipeline. I mean, I could go on and on. So the fundamental point here is that anything that has an on-off switch, that means it's electromagnetically driven, has the potential to be affected by a solar storm. And I'm going to let you see the movie because you'll see things that you haven't seen perhaps before. Power grid happens to be the most important signature of space weather that can be very devastating. Once you lose a transformer, getting that back online can be months and months. And so you are without power. So now there you see, you don't have an ATM. You won't have an internet. You might not have your favorite TV channel. as I say, precision agriculture depends on it. Oil drilling depends on it. So it affects everything in so many ways. It creates drag, right? So space station has to be periodically boosted during solar maximum if there's a solar flare, and which creates a drag condition. Sensitive electronics on spacecraft have to be protected. So that's why forecasting space weather is very important, because we can't stop it from happening, but we can take mitigating steps. Next, please. So there were some game changers that we began to understand in early 70s, post the launch of Skylab mission, the first solar laboratory in space tended by astronauts. And what are some of those key understanding? So if you can continuously hit return, and I'll tell you when to stop. The corona is hot and controlled by magnetic fields, and it basically generates the entire electromagnetic spectrum. Most important, X-ray and extreme ultraviolet variability at Earth. This is called the NOAA R scale, and I'll talk about it again. High-speed solar wind originates from coronal holes, dark regions near the poles of the sun. Solar particles emerge from there, they impact Earth. This is the NOAA S scale. This is what creates radiation hazards. And next, please. And this is the big one we didn't know at all. Mass from the corona is ejected into interplanetary space. Solar catastrophic events can impact Earth's magnetosphere. It can really squish it, create electromagnetic fluctuation that generates current that propagates through soil and can cause transformer malfunction, power grid outage, also all sorts of stuff. These are the knowledge that came from Skylab. By the way, this year was the 50th anniversary of Skylab. Next, please. Go back here. So these are just some societal impacts that, by the time I'm done with it, you're going to know everything you have to know about space weather. So what are the societal impacts of solar variability, human radiation exposure? We have space stations, space exploration and utilization, high altitude flight, aviation. All those are part of that. Impacts on technology. We are talking of space systems, communications, navigation, ground infrastructure, all of it. And then we have terrestrial climate too, both short and long term. Now, of course, when we talk about climate, we talk so much about the greenhouse gases that we forget about the biggest source of climate anywhere in the solar system. And then there's particle radiation that pose significant hazards for astronauts, satellites, aviators, and passengers, and affects other planetary bodies. And increasing galactic cosmic ray fluxes near solar minimum highlight the increasing radiation hazard. So you can see neither solar maximum nor solar minimum is a good place to be when you're thinking of all of these space weather hazards. Next, please. So another picture, society is becoming increasingly susceptible to its space environment. And I don't know that you can read this, but there is GPS system, there is satellite operations, there is space operation. Of course, aurora is probably the most beautiful thing of this. Then we have aviation, we have power grids, and we are explorers. We are kind of moving forward with exploring space. And I say that you cannot explore space without the knowledge of heliophysics. When you leave the cocoon of the magnetosphere, you are in deep, cold space, and space is harsh. That's where, so we are mostly barricaded by all of this because of our magnetosphere. But it won't be the case on the moon. or on our journey to Mars. Next, please. So what are the primary drivers of space weather? Well, of course, I'm going to blame it on the magnetic field. If the sun was without a magnetic field and as boring a star as most astronomers think, I'm sure our Chandra physicists think so. The sun is, it's just an ordinary star. But this magnetic field creates our space weather. So solar flares happen. That is the most explosive event that we have in our solar system. When a flare happens, it produces energy along the entire electromagnetic spectrum. They arrive in 8 minutes. The most important ones are ultraviolet and X-ray radiation. And basically, they ionize the ionosphere. They create the neutral density into ionized atoms. That affect radio communications, navigations, all those sorts of things. This is called the NOAA R scale. Then about 30 minutes later comes the charged particles, which are solar energetic particles. Now, they arrive a little bit later because they have mass, and so they don't travel at the speed of light, but slightly slower, right? They can last for several days, affecting astronauts, spacecraft, airlines, radio communication, just like I said before. Then there is high-speed solar wind, which is common during solar minimum, slightly different phenomenon depending on the nature of the structures on the sun. And then finally, we have the coronal mass ejections, which is expulsion of matter and magnetic field. They arrive in 1 to 4 days, last a day or two, cause geomagnetic storms. And geomagnetic storms are the ones, like disruption of power grid, right? Navigation disruption, GPS disruption. That's what we are talking of. So these are your fundamentals of drivers of space weather. Doesn't matter where you are in the solar system, you're going to respond differently to these different conditions, but they are all going to be thrown at you. Next, please. So this is just a picture, from 22. I think the solar cycle sort of on the rising phase, and now it is. We are very much in the solar max phase in 2024. And on the lower right-hand corner, you see the Parker Solar Probe. During that time, Parker had entered an unexplored region even then near the sun, completing its 12th close approach on June 1st within 5.3 million miles of the surface. On December 24, 2024, Parker is going to get to its perihelion, the closest distance to sun, within 4 million miles of the surface. Nothing in history has done this before. And what you are seeing there is data. This is one of my closest mission. I think I stayed at NASA headquarters to see this mission happen. And we didn't get to this data till we got really close. So I was almost wondering, did I do it right? Should we have done this mission? What Parker is showing is going to rewrite in the way the corona is heated and the solar wind is accelerated. It's quite incredible. The other reason I'm showing this slide is that there was some small coronal mass ejections on January 29, 2022, and which impacted Earth's atmosphere. And we don't report everything, but whenever there is something big, of course, we inform the launch services and everyone, and through NOAA, we work with NOAA closely, right? And so these small CMEs, they were successive, increased drag at 210 kilometer altitude. SpaceX launched Starlink satellite, hours into the storm, leading to the re-entry of, over 38 of their maybe 48 satellites, because they didn't have sufficient drag to their thrusters. They did not anticipate the drag that would be caused by these small scale CMEs, causing, significant millions of dollar losses. So what the takeaways are basically, minor storms like this occur about once a month during this phase of the solar cycle. Larger storms are expected to increase, and we are already seeing that. We have seen many. And so we have to watch out. We have to know what systems we are applying into this environment. Next, please. How much time do I have?
We're at 7:38.
Okay, so I need to go fast. So this is kind of showing the progression of solar cycle through sunspot number. And you can see that the red line, which is for cycle 25, that was the prediction of a NASA NOAA panel. And very clearly, we have overshot that significantly, that we had to change that finding, basically. So it tells us what? That we still don't know how to predict solar cycle. Now I want to show you something else. We talk about space weather a lot, right? And space weather forecasting extends to other planets. But it also is important to remember the climate research, exploring long-term changes in planetary atmosphere, which is driven by solar activity. Solar radiation, magnetic field variation, sunspot, and cosmic ray shielding influence climate over decades to millennia. And, there's recent research, if you look at them, considers how space weather affects other planets, such as Mars's atmospheric density, tightens cloud cover and temperature, shifts on rocky planets. Understanding these interactions help us address similar questions about Earth's climate. So we are learning from these systems, from each other. Now, I want you to kind of look at the picture on the right-hand side, okay? So we talked about the fact that the sun appears constant, okay? And that's because we see the sun in visible light. Now, what I have done in that plot is actually plotted ratio of spectral solar irradiance from solar max versus solar min. And the green line there you are seeing basically shows very small variations when you go from solar max to solar min. And that's what we see. And therefore, the sun appears pretty constant and dull. But if you go to the blue side, which is the ultraviolet, extreme ultraviolet, etc., that spectral irradiance varies significantly from solar max to solar min. But it's not just from solar max to solar min. It could happen in a day. You get a massive solar flare, and this would just shoot up and change the ionospheric condition, which will change the photochemistry below. All sorts of things can happen. So it's not just total solar irradiance. We have to pay close attention to spectral solar irradiance. Next, please. So, we have to remember that most people think that solar max is a time when bad things happen, when space weather happens, or very interesting things happen. And solar min is when sort of sun has gone to die. Well, not true at all. But it is just human psychology. When we plot things in XY axis with maximum on Y axis, right? A maximum and minimum on Y axis, that's kind of a natural way we tend to think. So I decided that I'm going to really plot solar cycle sideways, where there is. So basically, they are two extremes, both minimum and maximum. And space weather actually is like Earth's climate oscillations, right? Solar activity fluctuates, impacting technology and health differently across both solar minimum and maximum. So blue is minimum and red is maximum. And we experience different kinds of space weather conditions during both phases. So sun never goes to sleep. We have space weather happening all the time. and they affect different areas, different items. It's never safe to go into deep space, but we will. That's kind of our propensity, right? We want to explore, and we have to have good forecasting to do that. Next, please. And so this is kind of, we entered a new era of interplanetary space weather, and this became possible with the launch of 2 stereo spacecraft, which have gone around the Sun-Earth line around Earth. They launched in 2006, and then came Solar Dynamics Observatory, fixed along Sun-Earth line. And with these 3 spacecraft, we could see the front and back of the sun simultaneously. Never before in the history of humankind have we seen the far side and the front side of the sun at the same time. And this basically, so 50 years ago, protecting stuff around Earth meant safeguarding everything around Earth, Earth's assets. Today, it means predicting space weather throughout the solar system to protect probes and future human explorers. And so SOHO Stereo SDO, giving us that view and the data, have led us there. Next, please, if you show the movie. And so this is now we have entered basically this zone of interplanetary space weather, where we can actually do accurate space weather forecasting. It's a cool picture. There is more, but since I'm running out of time, let's go to the next slide, please. So this is the new paradigm. With all the data from all those missions, okay, we are now able to create sophisticated computer models that can tell you exactly when a CME, a solar storm, is coming your way. This is getting more and more robust, and these are physics-based tools, pretty amazing. So we understand that accurate interplanetary space weather forecasting is essential for both robotic and human exploration. Next, please. Now, many of you have heard about Carrington event that happened in 1859, a solar flare so intense that it lit up the telegraph lines. And the question has always been, have we experienced a solar superstorm? And it seems like maybe we did. On July 23rd, 2012, one of the fastest CMEs of the space age basically rocketed away from the western limb of the sun, traveling at a speed of about 3,000 kilometers per second. Now, if you look at the right-hand picture, fortunately, you'll see that the stereo A was in the line of fire of this CME, and the spacecraft was hit by a severe solar radiation storm that we hadn't seen since 1976. So it wasn't Earth-directed, and we do not know if this storm had hit Earth, where we would be. There are all kinds of speculation, but it didn't reach Earth. So we don't know what it would have done. Stereo A survived and had a front row seat to all the data. And so we have been able to advance our science significantly. Next, please. So the next frontier in space weather basically is forecasting involves the uninterrupted tracking of storm clouds from the sun to the planets. And this is, stereo is actually gave us stereoscopic view, 3-dimensional view when they were in close range to each other. So stereo's heliospheric imagers monitored the sky at large angles from the sun, but the bright star field and galaxy often outshine faint CME structures, limiting basically direct imaging and understanding the space storms. These are some of the most amazing set of telescopes we have. Stereo's telescopes have a dynamic range of 10 billion times greater than the human eye can capture, okay? It can capture everything from the intense solar flares to faint objects like asteroids, offering unparalleled observation capabilities. We have lost stereo B, but we need more assets like stereo. Next, please. Very quickly, this is just pay attention to the lowest part of this plot, and you see comet, that is comet Encke. And we have a very similar plot for the new comet that showed up in our October sky. But you can see the comet's tail being disconnected. It's not by solar radiation. It is magnetic reconnection. These were not signs we were planning to do with stereo, but it is incredible it came our way. Next, please. Next.
Slowly coming your way.
Okay. And if you can hit a couple of more times. And one more. Yeah. So the top picture you already know. We have created these sophisticated models, interplanetary models, and now we can do that for exoplanetary systems. So for fun, red dwarfs make up about 80% of Milky Way galaxy. And we think habitability means being in the Goldilocks zone, having water in liquid form. Well, that kind of got shot to pieces with the results from the plots below. The plots below, what they are showing is on the blue is your exoplanet, okay, red dwarf star, and is that and then on the right hand side is your planet. And so the space weather conditions between this red dwarf star and its planet, which is in the habitable zone, so could have liquid water, is still very lethal because the space weather conditions are so severe that it can strip up the planet's atmosphere, which means no life. So there are many things to consider now as we think about exoplanet and habitability. Next, please. So heliosphere, just as the Earth is protected from solar energetic particles by its magnetosphere, the solar system is protected from galactic cosmic rays by its heliosphere. Basically, the bubbles surrounding the Earth and the planets that is created by the solar wind and magnetic field. Next, please. And so this is astrosphere, just like sun has heliosphere, other stars have astrosphere. So on the left-hand side, it's a picture from Hubble of an astrosphere. In some ways, it almost feels like it's a fractal, right? So our planet has a magnetosphere, our sun has a heliosphere, stars have astrospheres. We all have some magnetic bubbles around us, at least if we survive, if we are a species. Next, please. And so this is very interesting, cosmic rays that I've been talking about during periods of low solar activity, cosmic rays can penetrate deep into our atmosphere. During high solar activity, solar magnetic field strength is high, and so it's able to deflect the cosmic rays. And, according to the NIH, so if you are a 1K flyer, we receive a dose equivalent of 20 chest X-rays. Something to keep in mind. And according to NIH, a chest X-ray gives a radiation dose similar to, say, 10 days of natural exposure. So a 1K frequent flyer receives equivalent of 200 days of natural exposure annually, about 50% more than average. And if you are doing a 13-hour polar flight from Chicago to Beijing during low solar activity, this delivers roughly the dose of 2 chest X-rays or 20 days of natural exposure. So all of this extra radiation may slightly increase long-term risks of cataracts, cancer, though effects are not immediate. NASA has created nowcast of atmospheric ionization radiation system to keep track of what's going on. Next, please. So not only Earth, but the entire solar system lives with its stars, captured through many of our satellites' beautiful imageries. Next, please. And so like Earth, planets have auroras that respond to space weather. Some are very much the very same physical processes, but not all. Next, please. And so both our terrestrial planet neighbors may have once had oceans and more Earth-like surface conditions. The question is, what happened? Both also have weak planetary magnetic fields. Did those fields and space weather play a role? It is an important question to ask. Is magnetic field sort of a precondition to life, to habitability? Next, please. So this shows, the atmosphere of Mars, being ripped off. So going back, a planetary magnetic field makes a difference. So Mars faces severe consequences without a magnetic field, which it lost less than 1 billion years after its formation. We don't know why. Now, solar wind particles strikes Mars at nearly 1 million miles per hour, causing atmospheric particles to escape. So Mars currently loses, and this is from MAVEN mission, about 100 grams of atmosphere every second. And during intense solar events, this loss can increase to 10 to 20 times. This is how a planet becomes perhaps inert, lifeless. We don't know, but this is what we study. I'm going to change tune and go as fast as I can. And this is going into now a little bit about, next please, accelerating open science, right? So basically, space has vast amount of data that we haven't utilized from decades of missions, and amazing opportunity to apply artificial intelligence and deep learning in particular to that data in new ways. And I think there are discoveries right before us that can be gleaned from the data that are beyond the capacity of our mammalian senses. That's what makes it so very interesting. Next, please. So what is NASA doing with big data? NASA gathers approximately 2 gigabytes of data every 15 seconds from over 100 plus currently active missions. And we do this every hour, every day, every year, and the collection rate is growing exponentially. So you can imagine handling, sorting, managing this data is a massive undertaking. But our data is our most valuable assets. That's why we fly missions. This is what gives us an insight into science. Next, please. So I want to show you this cool multidimensional GIF. So I want to talk about AI, right? Let's start with the basics. So artificial intelligence is just probabilities, but with vast computational resources like the rise of GPU, what are its values? It can repeat onerous human tasks, things that used to take scientists months, years, but also it helps us make sense of complex patterns beyond the reach of our mammalian senses. Just look at this. These dots look ordinary, but they have underlying pattern. AI tools extract patterns from complex multidimensional data, enabling new insights in space science and heliophysics. This was like a simple example I wanted to show you. Next, please. So this is our systems observatory. These are our data set that we use, 20 operating mission, 27 spacecraft, crisscrossing the distance from the sun to Earth and all the way to the interstellar medium with the Voyagers. Next, please. And this is a visualization that presents orbits of the current heliophysics satellites that cover the space near Earth out to the Sun-Earth Lagrange point, L1, a very important point, gravitationally neutral, about 1 million miles from Earth, and some of our current operating missions. They are all color-coded. Magenta is thermosphere, ionosphere, mesosphere. Yellow is solar observation. Cyan is geospace, and magnetosphere. Violet is heliospheric observations. But I am going to move on. Next, please. So let's talk about the scale of data, right? I mean, just look at SDO. All the other missions you can't even see. DKIST is a National Science Foundation mission. We are not responsible for it with a huge amount of data, but SDO is our biggest data source. And right now there is 8.7 petabytes of compressed AIA images and products, okay? Uncompressed, all of this turns out to be something like 22 petabytes right now. Okay, now how big is a petabyte? 11,000 4K movies. It would take you over 2.5 years of nonstop binge watching to get through a petabyte's worth of 4K movie. That's what we are dealing with. And that's why we want to use AI. Next, please. So, deep learning's capability to process large data sets enables better, more accurate space weather predictions. Bottom line. That's why that blue line with new AI methods, deep learning, it keeps on rising as you give it more data. The lower line, which is the other line, most other algorithms has already plateaued. So this is an incredible tool right now. Next, please. I want to show you a few examples very quickly. So this is Solar Dynamics Observatory. It has 3 sets of 2 telescopes and an instrument. One of the instrument lost a sensor in 2014. That sensor was producing actually spectral irradiance of a certain range that is really important for ionosphere because that's a direct proxy of energy input into ionosphere. So the question we asked is, can we use all the other images from Solar Dynamics Observatory and use AI tools to recreate synthetically, what we cannot see anymore by losing what we call the MEGSA. And that's what you're seeing. You are seeing the architecture. ML is used to compute how the sensors pass readings. So basically you have SDO data for ML architecture, which is on the left. And the output is MEGSA spectral irradiance, which is all those lines you are seeing. And this is quite incredible when you actually compare it to other such data. And of course, you're doing validation and verification. What this also showed that this particular approach outperformed physics-based differential emission measure way of calculating spectral irradiance. And this work was done over 8 weeks in summer by graduate students. Next, please. Of course, with a lot of help from mentors and compute resources. So it's the same thing, once you have like a machine learning data set, and we have that for SDO, not the 4K by 4K resolution, but by 512 by 512, we can do auto calibration on the left, which identifies sun patterns to correct for instrument degradation, potentially reducing the need for costly suborbital calibration launches, because that's the only way we can do calibration. Then on the right-hand side, we can do thermospheric density predictions. So this is 93 million miles away. We created some synthetic data. We use ML data to build accurate, fast thermospheric density models with uncertainty estimates, enhancing orbital drag predictions. And it's much better compared to existing models. Next, please. Star spots. What can we learn about heliophysics from stars? ML processes star data from Kepler and TESS, revealing star rotation rates and characteristics of extrasolar star spots. These are amazing. I can't go into details, but I'm just throwing them at you You can go to frontierdevelopmentlab.org and find and read about a lot of this. Next, please. So new capabilities are emerging every year. So we have to look at what's new for each year's FDL. Next, please. So the question here was, how can we observe the sun and solar irradiance from any perspective? Because we are limited to being in the ecliptic. You know, we have SDO and we have stereo. Okay, next, please. This is a poster, and I'm going to let the poster just stay there for, few seconds. So any of you who is interested in this work, because this is pretty amazing, you can go back and look at it since it's being recorded. Next, please. So what did we do? We found this new tool called neural radiance fields, NORFs. And, this is a method, it's a mathematical method that achieves state-of-the-art results in 3D scene representation. The method uses input images from a number of different cameras, much like we are trying to do. And by optimizing a model, it achieves to render new views. And that's what you're seeing. So we applied this technique to SDO, stereo, A and B, when all three of them existed together. And we call it solar NORF. Next, please. Voila. And that's what you have. You are seeing the sun, solar irradiance in 3D. And all these observations that we used are obtained from ecliptic. We can use this method to even reconstruct, consistent observations of the solar poles. This is kind of fun. It's not magic, it's real, it's mathematical. Next, please. And I'm very close to the end. These are kind of, we can get solar irradiance as long as we have the data in any place in the solar system. And that's what you're looking at. And next, what I'm going to show is Sundar Pichai. Google has been really providing compute over the last 7 years for all the experiments we have done with AI at Frontier Development Lab. So I would let him speak to it. So if you can go to the next
Cost efficiently. This speeds up response time, helping get people and resources where they are needed most. Likewise, Frontier Development Lab, in partnership with NASA, Google Cloud, and others, has created the first 360-degree view of the sun. Using AI, they combine data from 3 NASA satellites, making it possible to observe the sun from any vantage point. This will help scientists better predict the impact of the sun's activity on our planet. They're also using AI to see the moon's permanently shadowed regions as if it were daylight, an important step in lunar exploration.
Next, please.
Finally, they've built models that...
And so this is my last slide. Well, sun touches everything. I hope I have impressed upon you that study of heliophysics affects diverse fields, including human exploration, aviation, space situational awareness, biological and physical research, you name it. Thank you.
Thank you. It has been an incredibly long day here, and I'm so glad I've lasted this long because that was really amazing. I want to say thank you. As a geoscientist, I already feel small. A lot smaller now.
But we are all connected.
Yeah. Yeah, there was a few things. There's not too many questions in the chat yet, but I have a feeling we're all in the same boat in terms of processing everything. So to the history of heliophysics, is it safe to say that until the industrial age, when we were really focusing on our electronics and our communications, that it really just it was just another thing in the sky?
Well, we looked at each one of these areas separately. So we studied the sun in great detail. We looked at the ionosphere, Van Allen probes. I mean, some of NASA's early experiments, Explorer 1, 2, etc., they were actually probing all of these different regions, right? But they were not connected. As the sun-Earth system, that is what heliophysics became. And that's the same as sort of the observation and interrogation of Earth as a system that happened under International Geophysical Year.
Yeah. So bringing my own, I'm a geologist. And as a geologist, I love the part in class when we start talking about Earth's magnetic field and our magnetic reversals. Is there a connection between the magnetic fields?
Absolutely. So, it is the connection, basically, we should call it magnetic reconnection between sun's magnetic field and Earth's magnetic field that allows for the particles to propagate in. So completely, and the reversal process, when it actually happens. So imagine that Earth's magnetic field, now the poles are at the equator.
Mhm.
We have no shield. So, everything
Right.
else is going to bombard in. There are a lot of interesting histories here, things we don't know. We are understanding. And if we could go back and kind of capture that process of reversal of magnetic field line on Earth,
Mm-hmm.
along with solar observations and everything else, who knows? But remember, we didn't care what the sun did. It's our technology that told us.
Right.
And because we have become so vested on technology, now there is no separation.
So we do have a question in the chat from Julia. And Julia says, can you talk about the Helga and Zahar? Are the measurements taken now used to plan for radiation, and how?
I do not, unfortunately, know what she's referring to about Helga and Zohar. What radiation measurements?
Sure.
Is that from Eastern Europe?
Julia, feel free to elaborate if you wish, or unmute and ask.
Hi, thank you. I was reading something and it said that the Artemis mission had mannequins named Helga and Zohar.
Okay, all
And
right.
it's something about radiation, and it sounds very it sounds like the research that you're doing definitely has a direct impact on that. And I was wondering if you could comment on that, and then maybe future missions, and if there's going to be something similar.
Thank you for enlightening me with those two names. I didn't know. But of course, Artemis mission, that are being planned, we have radiation sensors. Hermes is the name of the instrument, flying from Goddard, so we will be doing that. We have radiation sensors aboard International Space Station. We have had BioSentinel that is taking radiation measurements in space. In fact, just this year, we did a Frontier Development Lab activity, kind of collecting some of this radiation and trying to see whether we can use the solar data that we already have in AI-ready form. We got some really unbelievable results. So this is an ongoing activity. Radiation is something, I don't know how we mitigate around other than being able to forecast and taking mitigating steps right now. So we are definitely on it with many different kinds of instruments.
Thank you. I don't want to hog the chat and the questions, but you mentioned you just mentioned the International Space Station. Those two astronauts that are there till, I don't know, February, do they have increased risk from the
So,
radiation, and is that being measured?
absolutely. So that, all of the research that we do, we share with NOAA. NOAA is the nation's sort of forecaster for providing this information. We also have at Johnson Space Center doctors and scientists who are monitoring the astronaut health. Most important, and so if there is a solar storm coming with a high level of solar energetic particles, right? There's space in the space station. It's not lead, but water, that will thwart the motion. So astronauts are basically kept in safe harbor once we know. If there are EVA activities going and we find out from forecasting, they are brought in. So for predicting solar energetic particle radiation, the safest thing we can do is give people an all clear signal that nothing is going to happen over this time. But, our physics knowledge is not sufficient to even do that. So we need data all the time.
So how often, just to follow up on that, how often do you think researchers are taking account of space weather when they're looking at some more of the sensitive data that
All
they're
the time.
Yeah.
All the time. If you're launching something, you don't launch.
Right.
You look at the weather and you look at space weather.
It's interesting.
And that's why I gave that example with Starlink. They kind of took a risk.
Yeah.
But still, the CME was small and one didn't anticipate the kind of drag it caused.
I actually wrote that down because I thought that was incredible. I never even imagined the solar storm causing that much drag to have that impact, literally.
I think I've tired everybody, including
I think we're
myself,
all,
probably.
no, I think we're all in a, like,
I'm happy to stay on if there are.
you grow up with a sun around you, and we know NASA does these wonderful things, and I just don't think I've ever, as a geoscientist, considered how linked everything is. We speak about it, but you did just an incredible presentation. I think most people on this call are probably still processing, because it's amazing.
In the future, I'm sorry, this is Julie again. In the future, I've noticed that on this presentation and other presentations, it seems like presenters feel the need to fit some sort of time constraint. And I wish it was a little bit more fluid, because some of those slides, like he said, like we're still processing it. I took pictures with my phone of some of the slides so I can go back and read them. But definitely, I mean, just that, they were just visually stunning. So thank you for that. I mean, it was just amazing. And yeah, I wish that presenters in the future would be okay with letting it go a little bit long. I don't know why everything has to fit in a 60 minutes or 30 minutes. It's kind of silly. But thank you so much. Those visuals were awesome. I can't wait to see the recording.
Hopefully that'll be up soon. I'm with you, Julie. I'd let people talk as long as they can, as long as it's interesting. And this would have gone on for days.
I had to pack a lot of things because, it's still very interesting that heliophysicists are not invited to talk very often.
Mm-hmm.
And I don't know why. We're the most interesting thing there.
Send us their names and we will bring them in.
Yeah, and you can delve into each part of it in great detail.
Okay, seeing no other questions in the chat, I really want to thank you. This has been wonderful. I hope we can have you back at some point in the future. Best wishes to everything, and for all of our attendees, it will be posted soon once we get it out of the cloud and onto YouTube, so you can watch it again. And like I said, thank you so much. It's been a pleasure.
Pleasure. Bye.
Have a wonderful evening.